Okay. He said left and right. Left and right. Okay, you're happy. Okay, great. Well, our next talk is by Ilan Gronau, and he's talking on reconstruction of phylogenetic trees with very short branches.
Okay, so this is a more recent work of ours, together with Shlomo, my advisor, and also Sahi and Hillary from Harvard. And this work seems to be quite a big project, which deals with phylogenetic trees with very short branches. Okay, so the basic paradigm in phylogenetic reconstruction is that we get an alignment of n sequences of length k, and we're trying to reconstruct the phylogenetic tree. So one thing we have to assume about our data is that it is consistent with some underlying real tree, which looks something like this, and the edge weights you see here, which makes it look kind of weird, correspond to the amount of evolution these sequences underwent on the tree. So you already see here that there are some very long edges and there are some very short edges like here. So what we're going to focus on is how these short edges make our work as in reconstruction. It makes our work a lot harder. We're going to try to make it slightly easier. So probably the main objective in this scenario is to try to devise good algorithms for reconstruction, and a good algorithm is supposed to give us good guarantees about reconstruction from which depend on the length of alignment that we provide. So hopefully the longer the alignment we give the algorithm, the more it is able to guarantee. This looks like a basic property that we want. So Candy talked about fast converging algorithms in the talk, and this is probably the major work which was done in reconstruction guarantees. And convergence really tries to deal with the minimal sequence length or alignment length, which is required in order to reconstruct the entire tree correctly. So fast converging algorithms really try to keep this threshold function to a minimum, so that we are guaranteed correct reconstruction of the entire tree from minimal length sequences. And one thing that really appears again and again in all these works is that this threshold function, which is a function of the structure of the tree, has a dependence on the minimal edge weight of the tree. This seems to make sense because if the tree contains a very short edge, this short edge probably has very little evidence in our data, and it's going to be very hard to reconstruct. And if you want to reconstruct everything, then it's going to be very tough. So the bottom line is that even these very good fast converging algorithms still require very long sequences in order to reconstruct these trees which contain very short edges. So this is not very useful from the user point of view, because we say, well, we have a certain sequence length, and we want to reconstruct as much as we can. So we wouldn't be able to reconstruct these short edges, but what about the rest of the edges? And convergence analysis doesn't really deal with that. So we want to think about something that is slightly more user-friendly, and we want a reconstruction guarantee that tells us, that in a sense, tells us what our algorithm is, what edges our algorithm is capable of reconstructing, and we want to maximize that for every sequence length, even if the sequence length is shorter than this threshold, which is needed to guarantee the correct reconstruction of the entire tree. So we thought of a generalization of fast convergence, which we call adaptive fast convergence. May not be the optimal name, but that's at least a temporary name. And the essence of this and what the algorithm is actually capable of guaranteeing. And this is a more flexible and maybe natural requirement than this one, because the user can say, I can only afford these long sequences, do whatever you can, and try to guarantee whatever you can. And this guarantee, in a sense, you can look at it as a false negative guarantee, which means, which tells us what edges are not going to be reconstructed, and typically it's going to be the short edges, the edges of weight less than epsilon. And there is a trade-off between, we want a very clear trade-off between the length of the input sequence and the length of the edges which we are not reconstructing. So two things about this threshold function. One is written here in red. We don't want it to depend on the minimal edge weight, of course, because if we have very short edges, we don't want to care about them. We want to be ignorant of these edges and still be able to reconstruct the rest. And another thing is that we want the behavior to resemble the behavior of this threshold function, in the sense that the dependence on the minimal edge weight here, we want to translate it to the dependence on epsilon, which is user-defined. This is the length of the edges that the user wants to reconstruct. In a sense, he's giving up on the short edges and wants to focus only on longer edges. So this looks like a very natural requirement, and we want the first probably stages to see if known algorithms follow this requirement. Okay, so I'm going to skip through this slide. This kind of describes our journey into trying to find an adaptive fast converging algorithm. And it's not, you see these X's, we were not very successful in at least finding among the existing algorithms an adaptive fast converging algorithm. And the main problem is this one. Well, first of all, we are seeking it among fast converging algorithms, because at least we know they are fast converging, and we only have to take care of the adaptive part. The problem with most fast converging algorithms is that they really focus on getting everything right. So they're not, so if they can't do it, then either they give up and say, I can't, or they do something, but it's very hard to see what they can guarantee. And in a sense, we can also find specific cases where these algorithms, the fact that they are wrong on the short edges, which is inevitable, it also propagates to longer edges as well. There are more likely candidates with our recent algorithms, which don't try to reconstruct everything. They try to reconstruct forests by kind of progressing from the leaves inwards, and they get stuck on these short edges. The problem is that they, like in a one-line argument, they may not reach some good edges, some long edges, which are buried in a sense inside the tree. So they're good in the sense that these methods are reliable, they do something well, but they don't reconstruct something that they're not sure of, but they can't guarantee us really anything. So after kind of despairing from these fast converging methods, we try to look at a method which we know is very reliable and has edge reconstruction guarantees, and that is Bunemann's method from 71. The problem with it, obviously, is that it's not fast converging, so it can't be adaptive fast converging, and the edge reconstruction guarantee it has is very poor. It depends on the maximum error, which will be very, very big. So it guarantees only reconstruction of very few edges, usually in a tree, and this is actually what it does. It really poorly resolves the trees, but does it very reliably. So that's a good thing. So I can conclude this journey in the fact that we couldn't find an existing adaptive fast converging algorithm, which actually makes this question more interesting in a sense, because it seems like we have a criterion which is natural, seems like what people want, and it's not trivial in a sense that simply by fast convergence you don't get for free pre-adapted fast convergence. So it's something that you have to work on. And I'll skip all of our work in trying to devise such an algorithm and just kind of show you only the final stage. So this is our algorithm, which is adaptive fast converging, and it's a distance-based algorithm, like most fast converging algorithms, but it also receives some more things into its input, which allows it to be adaptive fast converging. The important thing is that it receives the sequence length, which determines our confidence level in the distance. And the nice thing is that the user can also define the amount of risk he's willing to take. So the larger risk you're willing to take, you're going to reconstruct more, but with some probability of error which rises. We'll see that in simulations. It's very apparent. This gives our algorithm some very nice flexibility, and the user can define the amount of reliability he wants to put in the output. Another nice feature of our algorithm is that it has optimal time complexity. It wasn't very easy to get, but our algorithm is, I think, rather elegant, but it's not very simple, so I will have to skip all the details. Two things that I can say and are important to say is that, first of all, we guarantee zero false positive rate if our risk is low enough. So if our user doesn't take too much risk, he's not going to get any error in his tree. This is important, but it's without the false negative guarantee. It's trivial because you can always reconstruct the star tree and have no false positives. So we want a false negative guarantee, and this, in a sense, I think, is the first time there is an actual meaningful false negative guarantee, and this is given by adaptive fast convergence because we are able to bound the weight of the edges that we don't reconstruct. So we only miss the very short edges. So I can't get into more details. Hopefully I'll have a chance in December if you are here, and if you're impatient, then we have also a paper which we are writing, and I'll be glad to get into the details if anyone wants offline. So instead of getting into the details of the algorithm, I'll show you some very preliminary experiments which kind of I think give a good idea of how this algorithm performs on real data, which is simulated data. So we took some model trees from Pasquale's lab, 96 taxa, ran simulations using Juice Cantor, and then fed the distances calculated on these sequences to our algorithm and got trees. And now we played with the risk to see what this gives us, how this influences false positives and false negatives. And when I say we, of course I mean Hillary. So first let's look at what happens when we do it on an individual tree. So this is not a special tree, it's one of the trees in the data set. And we use sequences of length 300, which is rather short, I think, for such a big tree. And these are the results we get when we tune up the risk. So this, the x-axis is the risk, and the y-axis gives us the number of edges we miss. We have false positive, false negatives, and there's some, which is the Robinson-Folds distance. So first thing we see, we have what I call a safe zone, which is a zone with zero false positives, as we predicted. So if we use low risk, then we do get a zero false positive rate, which is very nice. And at this point, we already get about half of the internal edges, which is not great, but it is not trivial as well to get half of the edges without any errors. This is one nice feature. So after this safe zone, there's what I call the gray zone, and it is somewhere in the middle. I guess it depends on what you want, because the false positives start climbing but you still get a very steep decline in false negatives. So you're in a good place. The Robinson fold score decreases, but I guess it depends on what you want. If you want a very reliable tree, then you want to stop somewhere here. If you want a good RF score, then you'll be willing to pay with false positives. So there is an interchange here, which makes it good. And the final zone seems to be kind of very danger zone in a sense, because you get quite a steep incline in false positives, and no really the false negatives don't only stay, they even grow. So this is kind of a zone you really don't want to get into in this formulation. So this didn't look good enough for us, and we thought, what happens, and the problem with this thing is that you look at individual trees at different risks. What if you combine them? You can, so our idea is to combine them in a sense of ordered consensus. Because the trees here are more confident. The edges, we are more confident in them because we got them at low risks. And we know that there is a zero false positive somewhere here on the left. So we kind of want to put more confidence in the edges we get in the beginning, and only add the edges here which are consistent with what we already have. So we only accumulate edges which are consistent with our previous hypothesis, and the graphs for this strategy looks like this. So the dashed graphs are the earlier graphs, and we see a very nice improvement both in false positives and in false negatives. So first of all, so the false positives do grow, but not as extremely as before, and we cancel, and the nice thing is that the false negatives continually decline. So now there is meaning to all of this zone. It depends on what you want. If you want minimal false negatives, then you will be willing to go all the way to the end. If you want a more reliable tree with low false positives, then you want to stop somewhere in the beginning. So there is a question here of when to stop. So going all the way, you get this kind of result, which is good in terms of false negatives. Another obvious extreme is to stop the first time you see that there is an inconsistent edge. When you encounter an edge in these trees which is inconsistent with previous trees, then you can stop and say, this is too risky for me now, and typically you will get very low false positives at that point, and you can stop anywhere in the middle and get intermediate results. So I'll finish with some average kind of results on 100 trees, all of them 96 taxa. These are the three strategies we looked at, and we get more or less the same thing. Stopping after the first inconsistency gives us a very reliable result. Going all the way gives us the best resolution out of these, I mean the minimal false negatives, and in the intermediate kind of strategy gives us the closest tree to the real tree, but this is rather less significant. And we also compared it to other methods. So Goudeman is really poor, as we would expect. It has very poor resolution, but very high reliability. And neighbor joining, well, it's kind of hard to compare. RF distance is very, well, it's similar. It's even slightly better when we do this. But I think the take-home message here is not, well, we're not trying to be better than neighbor joining. We give a lot more information because we know exactly at which stage edges were added. And the earlier edges are more confident edges. And now we can use this kind of to assess our hypothesis, not just blur out the tree, but give more information on the edges as we do it. So to sum up, we had two parts of the talk. The first part talked about, a theoretical term of adaptive fast convergence. We stated that we have an algorithm. We didn't talk much about that. And then we saw we can use this algorithm to get some nice results. There are future works here. I just want to say one slight thing about the major challenge. So what we did, in a sense, successfully, is avoid these short edges, which is nice, but what we would really like to do is deal with these short edges, and we think that by at first stage avoiding them, then you get a topology which is reliable. You can use this extra information to actually deal with the short edges. So thank you all for that.
Maybe we could have one short question. Okay, well, is there a short
Did you
question?
try to refine tuning 3?
Well, we didn't have the algorithm for that, so we didn't do it, but does it give much better results than
I'm not sure. That's why I was asking.
My guess is that it gives slightly better results than Boolean, but not something very extreme.
A very simple strategy is simply to collapse the short branches. For example, you can give the neighbor turning. Have you made any comparison between this very simple strategy and yours?
Well, neighbor joining, at least in these experiments, seems to do not very bad. I mean, it seems like it's wrong generally on the short edges. So you could, if you took these edges, if you were able to indicate them, see what the short neighbor joining edges are, and collapse them, you probably would get a good result. The problem with neighbor joining is probably that you really can't prove anything. So it may turn out to give a good result, at least on these size of trees. My prediction is that when you go to larger size of trees, you'll start getting problems even with that. But it's probably a more fair comparison to try your approach and see if you get a better result in neighbor joining.
Okay, just one quick announcement before we head off to morning tea, and that is I really want to encourage people to please fill out their questionnaires and hand them in. The information is taken very seriously by folks here at the INI. Okay, thanks a lot.